you know, it's not optimal. I see now we have been dragging this like uncertainty quantification now for 3 lectures. Okay, we had our first one was on the 28th, then we had the last Monday we had the exercise, and today we are continuing with the exercise. So I hope you remember, because I struggle to remember what were we discussing at that time. Okay, but yeah, that's what we have, so that's what we have to deal with. So we have that problem, right? We have our estimation of total recoverable reserves. We know each input is not, now we have one number, but actually we have a distribution, and we mentioned how this distribution came, how did we came up with this distribution. Okay, we can either measure and then have like an educated guess. We say, well, it will behave in the same way from other projects. We can simply say, well, I don't know anything, can be from here to here. Okay, I can have triangular. And we use this called the Monte Carlo method, where we take a sample randomly, we run it, and we calculate this value. We take another sample, run it, and calculate the output. Okay. You can apply this with any method, any equation, any simulator, anything. Okay. The only restriction is that you need to have a high, we say high number of samples. Okay, 500,000, maybe 10,000, depending on your system. Okay. So it might be prohibitive if you have a reservoir simulator that runs in a day, for example, that you have to say, well, I have to wait 3 years, okay, because I have to make 1,000 samples. So, or you make it parallel, okay, I have 3 computers, then I have to wait 1 year, okay. So, and the idea is simply to get an impression of how this variable looks like, considering these probabilities, okay. And I told you it's equivalent to like trying to map how the function looks like in like a multi-dimension case. Okay. I told you that we have simply to increase the number of samples until you get some convergence. The frequency distribution of the output doesn't change much. Okay, and then you say I stop and I don't take any more samples. We see here, like in this example, it's something between 1,000 and 10,000. I might probably be satisfied. Okay. But I have to use, typically, I think that's something we mentioned last lecture, we typically have to use like what is called a convergence study. We have to increase number of iterations and see how my distribution is changing, or I say it's equivalent to say how P90, P50 and P10 are changing. Okay. We did this example in class, I think you did it, and I help you also. That we have to make, we can make these calculations in Excel. Here are all of our samples, here are our results, and then we make a frequency analysis of these results. Okay, and we end up with these results, the PDF, which is like a log normal, which is just like a normal, but you know, a bit tilted. And then we said, in petroleum engineering, we don't use the CDF, but we use the inverse of the CDF. And that people call it CDF, okay? Or they call it expectation curve. We just have to be sure that the actual CDF is flipped, okay? It's from small to large. But in petroleum engineering, that's what we call CDF. Okay? It's not exactly correct, but at least it tells you that the field has that probability or higher, okay? It's like you're in the optimistic side, you're not pessimistic. Okay, I show you some examples from the PDO of Hebron and this PDO of Karish and Tanin, some fields in the offshore Mediterranean. I told you about, if you want to read a bit more, there are some ways to estimate the number of iterations with a current simulation, and you can read that on the. And then we went straight to try to solve the same problem in Python. Okay, and that's where we left. Fast forward to the future, that's where we are now. Okay, because Excel is quite nice, we have visuals, like we can see all the points, but when we start to get a large number of iterations, 1,000, 10,000, then it's becoming heavy. You see that the sheet becomes almost freezes and then unfreezes, then you do another change, freezes, unfreezes. So it's much better to use a programming language or a software that actually doesn't show you all the numbers live. That's part of the challenge that Excel has. It's always trying to show you what I have on the cells. Okay, But if we had something that keeps it hidden, only showing when you want it, that you know, is a bit more computationally efficient. So we went into this. I'm not sure how many of you have done it, but we went into this CoCalc that I told you runs Python, and we started to use some Python. This is actually called Jupyter, which is a way that I can run Python scripts interactively. Okay, you can either put all of these instructions on a file and then run it, and then simply you get the output, you get the results. But here we can actually run block by block. Okay, so I told you in the first block, because I'm opening for the first time, I have to run all of them. So this tells me the green thing where I am. Okay, what have I run so far? So first I say import the libraries. This is for plotting. This is for it's like a mathematical library that we use in Python, and that is something for a table. I'm not sure we're going to use that, but just to make tables you use these pandas, okay, and for many other things. But if you are into all of these machine learning, data analytics, you probably are a big fan of pandas, okay, but we keep it for now. Okay. Then we say we declare the function, the only function that we are going to use, because all the other functions are included as part of this library, NumPy, okay, which is like a repository where I have a lot of functions available to my use, okay. Also plot. Here I have scatter plot, I have bar plot, I have X and Y, I have 3D plot, all kind of plots are in this library. And here I have these sampling functions for normal, triangular, all kind of distribution, okay. So I created that function and I put some comments. It's also nice to see what is the input. Then I say the input data, so let's run this guy. Okay, this guy shouldn't take any time. And this guy, I'm exactly writing the values we had on the Excel table. Okay, hopefully I typed them okay. Okay, then comes, I say I have to make the sampling and the simulation. Okay, so then simply, instead of having to stretch the cells down for each column, simply I call this function NumPy. I'm calling in this library, please go down and check the random module. It has a module called random, and under that module has a function called uniform, which if you give it a minimum and maximum number, and if you give it the number of samples, is going to spit for you a vector with many random samples in this range, okay, min and max. Something that is already pre-programmed for us, someone did it, and it's very nice to have, okay. After I have all of these vectors with all of these random variables, then simply run the simulation by calling this function with all of those vectors, all of those inputs. And I'm not sure if you have ever used MATLAB, but what it does, it takes the first element of that vector with the first element of this and so forth, okay, and then the second element and the third element and so forth. Okay, so if we want to, for example, simply that say how TRR looks like, okay, we are going to run it like that. Okay, and it tells you also a vector that goes from 77 million, or yeah, that's not the minimum, but okay, 124. You should have here 1,000 values, and it does it much more efficient than Excel. You see, it didn't. This is a server which is unpaid. It's telling me here, so it's going to have poor performance problems and still is quite fast. Okay, it's much faster than Excel. Okay, that's what we did last time. So what do we have to do next? We did the sampling, we did the simulation. What was the next step that we did in Excel? Okay, if we go back to our Excel sheet, to our Excel problem, we did our simulation, and then we had to make a frequency analysis of the result, right, of that vector. We have simply to start to make bins and to count them to see how they're distributed. Okay, so how do we do that in Python? Okay, and I call that frequency analysis. Maybe I should call it of results. Okay, I'm going to use here one method. There are a few other methods that we can use. Hope I don't. Okay, first I have to create, just in the case of Excel, I create the beans, right? And here the beans, they work in a slightly different way, beans. And the beans, for that I use a again a function in this library called numpy, okay, that is going to give me linear space from okay, and where should it be? Okay, what have we done here in Excel? In Excel, to create these beans, right, I had to first find the minimum and maximum. Okay, and then I had to create some delta or the number of beans, and then that's how it created this vector. Okay, so first we need to know the minimum and maximum of TRR. Okay, and that's very nice. This is a vector, so I can simply use in Python. Let's comment this for a while. Okay, and then we say TRR dot min. Okay, I think. Okay, and TRR, because it's like it already has, because has this vector, already knows that if I call this like function, it should pull all the minimum value from this vector. Okay, it's like that's an object and has that property, which is minimum, which is very helpful. Okay. Okay, so let's run it just to see what the minimum and maximum look like. Okay, that's the maximum, and that's the minimum. 35. Okay, so it goes from 35 to. So I say here, beans, please create linear space means equally spaced. Okay, as number of equally spaced points between the minimum, right, and between the maximum, and then I say how many points I want. Okay, how many beans I want. How many beans should we use? We were using here 30, I think, right, or 20. Let's use 20. Okay, the same number. Let's say 20. I think we were using 20 here. Yeah, 20. Okay, so that's going to create, calling that function is going to create simply a vector from min to max with 20 points. Okay, so if I plot now beans, or if I make it print beans, okay, went from 35, 166, and it should have 20. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay. What was the next step after I create the beans? Then I have to make this guy. Excel, you know, is feeling a bit jealous because we are using Python. So it says, why are not you using Excel? So then was this column, right? That I have simply to make the frequency count. Okay, to count how many do I have in each interval. Okay. So for that, we are going to use a function called np inside this numpy, okay, dot histogram. That frequency analysis, I call it also histogram of TRR, and I have to provide the beans are equal to the beans. Okay, that's like a parameter that I'm passing to that function. Okay. Quite straightforward. But that function is going to spit actually not one number, but it's going to spit two things. Okay, it's going to spit the histogram, the frequency count, and it's going to spit the beans again. Okay. Okay, so simply here I'm creating the beans, and then I'm counting how many inside this big TR. How do I classify them? And actually the way it's going to make is everything between 35 and 42, that will be in the first bin. Okay, everything between 42 and 49, that will be in the second bin. Okay, that's the way it counts. It doesn't count like in Excel that I mentioned. It creates like a midpoint between these two, right? And then say, well, everything to the left of the midpoint is assigned to this bin, and everything to the right of the midpoint is assigned to this bin. Okay? The way this function works is that everything in this range will be assigned to the first bin. Okay? Everything in this range will be assigned to the second. Okay, I run it. Maybe we should look how the histogram looks like, just to print it. Okay, and this should have 20. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Y has 19. If we have 20 bins. Okay, exactly because of the reason that I told you. It's the bins are used in between. Okay, let's plot again the bins, or print again the bins. Okay, we have here 20 values, but they are going to be counted between here and here. Okay, so that's going to be one bin. So you're going to be, when you make the counting, you're going to be one short, 19. Okay, that's this case in Python. Okay, Excel works a bit different, but just that we understand how this Python is working. Okay, next step, I have the bins and the histogram. What do I make? What is the next step? Simply plotting, right? I could plot it. Okay, let's create the plot in a different. So let's just run that box. Okay, and let's create the plot here. To create the plot, simply, that's not something you have to. Simply, you have to know the nomenclature. So I have to call this module called PLT. Okay, PLT, and I have to create first to that module. I have to give an X label. Okay, that will be the label of the X-axis. I'm going to say that will be NPU, right? And the units. And I think here we're talking about million standard barrels. Then I create the Y label. And here I say maybe number of counts. Okay. So simply I have created a plot, and I have put this label, and I have created to the same plot I'm adding the Y label. Okay, and what is the next step? Simply plot, right? Plot, and I want to plot the bins, and I want to plot the histogram. Okay. And then to show it, I have to PLT simply show. Yeah, I hope it works. Okay, I have the problem with the dimensions. I have to use these bins. Sorry for that. Maybe we should call it bins 1. Okay, bins 1. Oh yeah, because that's 19. Okay. Now we have to remove one bin, okay, because we didn't want to do that now, but now we have to make it. Okay. We have that issue is complaining because we want to plot two things that have different dimensions. Okay, the number of counts we're counting on this interval, which gives you 19, and the beans have actually 20. Okay, so we have to create a bean vector to plot it. Okay, that is actually in the middle. Okay, wanted to save that for later, but I have to explain it now. Okay, so now a comment for in the Python. Okay, the way bean works is that I give x1, x2, x3, and everything in between here will be counted in bean 1. Okay, and everything in between will be counted in bean 2. Okay, and it's actually quite a nice way to count, because then I'm not restricted if this uniform or not, right? I can give them that they might be equally spaced. Okay, if the user wants xi and then xn, he can make them equally spaced, or if the user can also count them with different spacing. Okay, can have very fine spacing initially, can have very big spacing later. So that's why they do it. But actually for plotting, we should have the mid value. Okay, this value here in between. For plotting, I should have actually x like 1.5, x 2.5, okay, x 3.5, and so forth, because I should plot actually the center of that bean. Okay, so one way to do it, and that's why we're having problems here. One way to do it, let's create the bean centers here, and this is going to be okay. So I say I'm going to write it, and then we see if you get it. Okay, and you see now we should have 19, okay, 5, and we are missing 1 here. So we have actually 19, exactly what we need. Okay, now what have we done here? I'm doing exactly what I told you here. Okay, I'm finding the half of the interval, okay, and I'm calculating this vector with half of the interval. So what is happening? What is happening here in this declaration? I'm saying the vector beans, okay, that was the original vector. I'm saying please take not from the beginning. Okay, the beginning is 0. Okay, indexing in Python and almost in any programming language. I think even Excel VBA is starting on 0. Okay, so don't take the first element. Take the second. Okay, from the second to the end. The 2 dots means from the second to the end. Okay, and this one is saying take from the first one, but don't take all the way to the end, but the one before the end. Okay, let's see this. I think is important. We spend some time here. Some of you that have been working with MATLAB before, that's probably a piece of cake. But for some of you that are okay, Okay, this sentence, if we have, let's say, beans are A1, A2, A3, and A4. Let's say you have only 4. Okay, so beans, if you say 1 to the end, that will be, what will it be? Will be simply A2, A3, and A4, right? And beans, if you have the 2 dots to -1, what will that be? That will be A1, A2, and A3. Okay? You simply are collecting, and that's a very nice way, very compact nomenclature to pick parts of this vector. Okay? You see, I use the brackets, and I use that looks like an eye, but that's actually 2 points. Okay? From the number 1, which is 0, 1, 2, 3, from the number 1 to the end, and here I take from the beginning all the way to the end -1. Okay? -1. So I make it nicer. There is no magic happening here, simply 0, 1, 2, 3, that is the index, okay, of each one. So like that, when I sum these two, right, and I divide by 2, I get the middle of the interval, right? The bean centers are A1 plus A2 divided by 2, okay, and A3 plus A2 divided by 2, and A4 plus A3 divided by 2. That clear? Yes? Okay. Now that one has 19, so that shouldn't complain. I'm going to erase that from here, so I get, and now I say please plot the bean centers, which is a better way, against the with the histogram, and I hope now it doesn't complain. Bean centers, okay, try to make it smaller, voila. Okay, number of counts and then NPU, and you see it looks like what we found in Excel. Okay, what happens if I increase the number of iterations? Now I want to make 10,000. What do I have to change in my code? Here, right? Number of iterations, 10,000. Then I have to run down to here. I use here run all above. Okay. And it did it quite quick, actually. Okay, looks much more smooth, but you see it didn't change much the value of the mode. Okay, maybe I can rerun 100,000. I hope it doesn't break. Okay, the same thing. Okay, I should get smooth this peak, but also with the bean centers maybe I can change to a higher number now that I have more samples. Okay. Okay, you can also call, instead of counts, you could also call it frequency. Okay, but then you have to, which it doesn't really make much of a difference, but then you have to divide the histogram, you have to normalize the histogram, right? And the histogram, then you have to divide it by n. okay, by the number of samples. Okay, and then it gives you a fraction, and usually that's how you make that's the PDF, and usually we use a fraction. That clear? Yeah, cool, right? I think it's cool, but I'm a bit of a geek, so I hope you think it's cool also. Okay, what are we missing here before we go to other things, other complications? The CDF, right? We need to have this, the cumulative. And how do we calculate the cumulative? So as a PDF of reserves, which is log normal, you see very clearly, you have the mode here, and you have almost like a normal distribution, but it's like tilted to the left. Okay, and that's how normally all reserve, they look like. Oh, maybe we can compare. I hope we get the same mean. Okay, mode around 80, okay, 90. Here we're getting a bit more to the right. Maybe we made a mistake here. Let's try with 1,000 samples. Let's try with 20. Every time you change something, remember you have to come on 80. Yeah, we're getting much less here. I don't know, homework. Okay, you have to find out why. It should give the same number. Okay, maybe we have made a mistake here. Okay, the next step is calculating the CDF. How do we calculate the CDF? We have to make a sum on this histogram, right? We have to sum either from bottom up or from top down. So for that, I'm going to use, I say CDF. Maybe we should call it, we forgot to put comments here. We say plotting PDF. Then we can make it just calculate the CDF here also. Okay, the CDF is going to be the cumulative sum of the histogram of this vector. Okay, and for that, luckily, I have in NumPy something called NumPy dot cumulative sum, and simply say this histogram. Okay, I already plot the PDF, and now let's create one more. Let's use a higher number of samples just to make it prettier. Let's use here 30. Okay. Okay, and then I have to exactly repeat the same thing, but now plotting the CDF. Okay, and for that we have to copy this part of the code. We say plotting CDF, and here we call it CDF or cumulative frequency, and I want to plot the same bin centers, but now I want to plot this CDF. Okay, just to check that you're awake, what does it mean here? I come 100, knock the curve, and gives me 0.9. What does it mean? 90%. There is a 90% chance, right, probability that my reserves are bigger or smaller than 100? Smaller, okay? Because you say if you go here to the extreme case 1, there is a 100% chance that they are equal to 160 million or less, okay? Because there is no chance, you have nothing bigger than 160. Okay, good. Okay, so you have to use, I suggest you to use Python for exercise, I think it's problem 5, right? Or 6 in exercise set 1. I suggest you to use Python and use this CoCalc. It will be much quicker than using Excel. Okay, you can use Excel, but you might have some, it might be a bit challenging. Okay, so let's open this exercise set. Okay, it's the last problem here, and you have to do the same thing. You have to combine this evaluation of n, but you have to combine it also with a cost equation that also has a lot of uncertain input. Okay, so I suggest you have to make either Monte Carlo. We're going to see now 2 other methods, but I suggest you to do it in Python. Okay, with this CoCalc. But you have exactly the same thing, but now this equation is inserted here. Okay, this equation, then you have the ultimate recovery, then you have inserted here in the cost, and then finally you insert it here. Okay, so you have uncertainty in all the volumetric parameters of the reservoir, but you also have uncertainty in the cost, and you have uncertainty here. Okay, so it's like a big problem, a lot of uncertainties, one kind of nested with the other. Okay. Okay. I think we are now 5 to break, so let's take a break now, 15 minutes. Okay, and we come back 10 to with the second part. Okay. So this method that was explained here, you can, I suggest that's what you use for exactly that for the problem. Okay, I'm going to show for the problem I gave you. Problem I think is 6. Okay. There are other methods to quantify uncertainty. One of them is called Latin Hypercube sampling, which is like Monte Carlo, but instead of doing random sampling, okay, a more like intelligent kind of sampling is made. Okay. And if you worked with, I think some of you work with Monte Carlo, but with Latin Hypercube, any of you worked before? Latin Hypercube sampling? No? Okay. So the thing is that you remember the plot we had before, right? That was x, y, and you had a function that's coming out of the, okay, we maybe put it like that, is z, and that's our function, okay? That is a function of, okay, I think mathematicians make it like that, x, y, and that is being plotted here. So random sampling or Monte Carlo sampling simply is making samples randomly in this space, okay, between, let's say, an x max and an x min. X max and x min, and then you have a y min and a y max. So it's trying to make a sample. Actually, none of these samples will be made. Okay, we're trying to make. So if you were having some more organized way to sample, okay, maybe your function by random initially covers just maybe part of it, or maybe will be spread evenly, but you cannot guarantee. They are random after all, right? So you might have that some of them you have a cluster, a cloud of points that they are maybe located in some region. Okay, so if you don't take enough samples, really, you're not going to capture the variability of the function of f, x, and y. Okay, so what Latent Hypercube makes is makes the sample in a slightly different way. Okay, when we have our CDF of the variable x. Okay. Okay, and we have our CDF, which is going to look like that, right? Remember, Monte Carlo was sampling randomly in any, can be any point, okay? Can be any, I can have random here, then random here, then random here, and that's where the problem comes. Because I might, the random generator might be just initially during the first iterations focusing in this area, okay? Maybe later, eventually we'll cover the whole range, okay? So what Latin Hypercube makes, just to make that like better, it says I'm going to divide these in some boxes. Let's say 5 boxes in intervals, okay? And then I say you're going to take one random number from each interval, okay? So you say, let me, if we're going to write it somehow, okay, divide the CDF in n, and these are the Latin LHS iterations, okay? Intervals. Okay? And sample randomly from each interval. Wow. Okay, so that means if you are in this interval, you sample here, for example, you are here in this interval, you sample, this will be your, for example, from 0 to, here we have 5, right? 1, 2, 3, 4, 5. So this will be 0.8, 0.6, 0.4, and 0.2. Okay, and simply sample any number between 0 and 0.2. For example, can be 0.11. Okay, any number between 0.2 and 0.4 can be 0.39. Okay, any random sample. Okay, in this case from 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, 0.6, 0.8, okay, and 0.8 to 1. I sample one random number in each interval. Okay, after I have that number, I read the x. Okay, I find the x. That's the first step, second step, third step. Find corresponding x's. Okay, so I come here to this and then I read this x. Okay, then I have x1, x2, x3, x4, x5. Then comes the step that means shuffle. Okay, I have all of these samples, then I shuffle. The fourth step is shuffle. Okay, that I mix them all together such that I don't know the order. Okay, let's say now in this case it will be, the vector will be x3, x2, x5, maybe x1 and x4. Okay, then I repeat for every variable I have. Okay, let's make it here 5. Repeat 1 to 4 steps, 1 to 4 for each variable. For each variable. Okay, let's assume now you have 2 variables. Okay, x3, x2, x5, x1, x4, and then you have another variable called y, that let's say here it end up like 1, y5, y4, y3, this shuffling will be completely random. Okay, I don't know where the numbers are going to end up. So let's say shuffle, this is a random shuffle. And then I say I take this combination with this combination, and this is going to give me my f x3 y1. Okay, and then I take these two combinations, and then this is going to give me another point f x2 and y5, another combination f x5 y4, okay, and so forth. The idea is that by doing this sampling, by doing the sampling in this way, I make sure I'm covering the whole distribution. Okay, and the other thing is by shuffling, making like a more, by shuffling, I'm making a more random sample of that. So I take random, so I try to cover the whole distribution, but then I randomize all of these vectors, and then I mix the first with the first, the second with the second, third with the third. Okay. And in this way, okay, and then you have the sixth step, which is the same as before. Do a frequency analysis on the results, okay, which are these guys here. Okay, what is the main advantage? They say it takes much less iterations than a Monte Carlo, okay, because you're making a kind of a more intelligent sampling. And there are all kind of samplings. You go to the literature, they use orthogonal, they use all kind of samples that people think is a better way to capture the space. The idea is that you need less simulations. You want to get the minimum number of simulations as possible. Okay, these are LHS simulations. Now this is a bit risky, but do you want to try to do it in Python? Huh? Yes? We try? Okay, I'm going to get into trouble, I know, but we try, okay? Okay. Let's so I go here. How do I go back to the projects? Okay, so I'm going to have the Monte Carlo simulation I made before, simply I'm going to duplicate. Okay, and I'm going to call it LHS to avoid making some of the things that, because the, okay, some of the things are the same. The main thing is the sampling, okay? The sampling now is going to be different. Let's say all of them are uniform, okay? Because I think the code I have is for all of them uniform, okay? None of them are triangular. And here there is a bit of kind of philosophy. I have to do this process that I showed you here, this sampling, all of this, dividing from 0 to 1. I have to find a random number. I have to read this number for each variable, okay, for each one of the things that I have, my porosity, recovery factor, net to gross, saturation, for all of them. So it's something that if I could make it one by one, okay, when I do the sampling I can do it here one by one, but then it will be, because it's always is the same process, right? So to effectivize, as something programmers said, if it's something that you're going to be repeating, for example, 7 times, more than one time, try to make it into a function, okay? Because if you, for example, do it by hand, I can do it very well, do it by hand, okay, one by one. But then I copy and paste, and then when I copy and paste and I change, I make mistakes, okay? So one rule in programming is, if I'm going to do many things repeatedly, and it's exactly the same process, the same operation, make it into a function, okay? So let's create a function for this Latin Hypercube sampling. Okay, and that function I'm going to call def, okay, Latin Hypercube sampling samples, that is going to give you the samples, and it's going to be uniform. Okay, what is that going to take? It's going to take n, which is number of samples. It's going to take the minimum value of the variable, and it's going to take the maximum value of the variable. Okay, and I'm not going to do it for the triangular, so I only need these two numbers. So what was the first step? Maybe here I can put some description of the function, what the function is doing. Returns a list of random values from a uniform distribution using LHS. Okay. And then a description of the input. N is number of samples to generate. Min val is minimum value of the variable, and max val is maximum value of the variable. Okay. So first, what do I have to do? Okay, first I have, let's go back, if we don't remember, we have to make that subdivision, right, from 0 to 1. Okay, so first I suggest we create a step. Simply, this from 0, here we have how many samples? 1, 2, 3, 4, 5, okay? So if we have 10, we have 1,000, we have 1,000,000, simply we have to divide that from 0 to 1 between the number of samples, right? So let's call it length of the interval. Okay, and that will be 1 divided by n, right? If I have 5 samples, simply divide it 1, 0 to 1 divided by 10. Okay, that is going to give me the delta of each one. Okay, and here I call it delta in cumulative distribution function. Okay. Next step, this is a bit tricky, right? We have created this delta, but now we have to say take a random sample between 0 and here, okay? And then take a random sample between here and here. Okay, so we could use, if you remember in the Monte Carlo, we have used this equation, right? Random uniform, okay? And you have to give it the minimum and the maximum. So I have to calculate the minimum and the maximum. I could use the same equation, but now calculating the minimum and the maximum of each interval. Okay, so that's what I'm going to do now. I'm going to calculate the minimum and maximum with that delta. Okay, so I call it interval starts, and here I will say use this useful function, which is np linspace, okay, between, when does it start? Interval starts at 0, right? And when does it end? Okay. all the stars of the interval, they start, one of them starts here, right? One of them starts here. One of them starts here, starts here, except one. Okay? So you should go from 0 to 1 minus the delta. Okay? And how many samples? 5. Okay? In our case, n. Right? So you should go from 0 to 0.2. The star is 0. The star is 1, 1, 2, 3, 4, 5. Okay? That's the start of the interval. Okay, so you should go to 1 minus length of intake. Okay? And how many samples do I want to draw? Or how many spacing, equally spacing values should I take? N. Okay? Here is just the starting value of each interval. Next step, that's the start of the interval. I have to make the end of the interval. Okay? Again, the same function, linear space, which is very helpful. Where should I start all the endpoints? According to this chart. The first endpoint is this guy, right? So it's simply the delta, this length int that I have made. Okay? That's the first point. And where should it end? This is the end for interval 1, this is the end for interval 2, this is the end for interval 3, end for interval 4, and end of interval 5. So you should go all the way to 1. Okay? So I say here length int should go all the way to 1, and I want how many numbers? N, right? Because I have, this is 1, 2, 3, 4, 5. The number of intervals exactly. After I have these, the start point and the end points, what do I have to make? Which function do I have to call? After that, remember, we said we are going to use the same as Monte Carlo. Monte Carlo is using this NP function, random uniform, okay, between a minimum and a maximum. So I say NP uniform, random, uniform, between interval start and interval end. Okay. And I call this the CDF samples. Okay? Remember, these guys are vectors. Okay? This guy has all the starts of the interval, and this guy has all the ends of the interval. So this guy, CDF samples, is going to be also a vector. Okay? And it's going to apply, this is the nice thing, vectorizing the function. So it's applying it to the first two elements, to the two second elements, and so forth. Okay? One by one, interval by interval. Okay, so if we're going to write that, let's make a comment on that thing. Okay, NP. So we have the interval start x1, x2, x3, x4, and x5, for example. That is the start and that is the end. Okay, and here we have in our vector will be interval start. Here this vector will have x1, x2, x3, and x4. Okay, and the interval end will have x2, x3, x4, and x5. Okay, And when you apply the function, okay, this np random uniform, okay, you apply it to these two vectors. This is equivalent, okay, to applying np random uniform to x1, x2, okay, and then you repeat, you find a number here, then you apply it once more, np random uniform x2 and x3, okay, and so forth. Okay, that's called vectorized function vectorization. Function vectorization. Okay, why is it pulling one number? Why here am I going to get just one number? Okay, let's say x star. Because if you remember, in Monte Carlo, I had to give the minimum and the maximum and the number of samples. If I don't give the number of samples, it's going to pull just one random number, okay, because it's missing the number of samples that it has to take. That clear? Okay, it's a bit of a hassle, but we are getting there. I warn you, kind of. Yeah, what is the next step? What does Latin Hypercube say we have to make now? Now we have made the intervals. Now we have picked the random number. What is the next step? Have to get to this curve and get this number, right? For that, I'm using this method, but I'm maybe not sure if it's the best. Okay. We call another library called SciPy. It's a library for scientific programming. Has solvers, has all kind of things, but also has a module for statistics. Okay, this is scientific programming library, and in particular statistics. Okay, SciPy stats, and I'm importing that as scp stat. Okay, SciPy stat. Probably have to run this guy. Okay, and then I say for each one of these CDF, I want you to read the number of the variable. Okay, and to do that instruction, I'm going to say samples. I'm going to save the output in samples. scp stat. I'm going to say that's a uniform. Okay, ppf probability function, and then you have, I have to give the input, which is the CDF samples. I have to say input the minimum value, and I have to give the length of the whole interval. I have to give, it's simply a way to call the function. Okay, I have to give the length of the between the minimum and the maximum, and that range I give it has I think it's called scale, and that is max val minus mean value. Okay, don't try to simply, that's the syntax. Okay, that's how the function looks like. This function simply, the only thing that is doing is coming with this curve and using this input and giving you this output. Okay, finished. Okay, and that's the way you use it. You call that library scp stat. You say that you want to sample from a uniform. You want to get what you're giving is the cumulative probability, and you give the CDF, the minimum value, and the range. Okay. What is the last step? After I get the samples, if you remember here in Latin Hypercube, after I get all of these samples, shuffle, okay? I have to make all of them random. I have to switch them places in a random way. How do I do that in Python? np dot random dot shuffle, okay? And simply of this function I want to return the sample vector, samples. Okay? Just note, I'm not doing any calculation here, no calculation. I'm preparing this function to take for every variable, minimum and maximum, a number of samples is going to give me already the shuffle vector, okay, with all of these samples. Okay? And that's something that I could have just made it for each variable, okay? But then I have to copy and paste this, and it might make a mistake, you know, it's less efficient, so it's better to keep it as a function, okay, as a def. Okay, I hope I didn't make any mistake, but if not, we will find out very soon. Okay, so let's see here, the functions declaration. Now I have the input variable declaration. Okay, you can do the same probably with triangle, but then you have to create another function called triangle. Okay, distribution. I also leave it to you you're getting a lot of pending tasks, okay, on your to play with it. Okay, what is the next step? Now we call it Latin Hypercube simulation. Okay, I'm not doing random sampling. How many n's do you want to take? Let's take 1000, okay, the same that we took for Monte Carlo, and we try to reduce it to see what happens. Okay, we have to take a sample for each variable. But now the sample won't come from this. This was from Monte Carlo. Okay. Now we have to use this equation. Okay. Okay, and I think here n was first. To make our life easy, maybe we can change the order here. Okay, and then I just have to copy this and substitute for each one of the variables. Okay, so now the samples won't come from Monte Carlo. They are going to come from this Latin Hypercube procedure. Okay? From this function that I have created that unfortunately is not available in the maybe not in this kind of mainstream libraries. Okay, maybe there is some person that programmed this in a generic way, but I didn't find it. Okay, for the class. After all of these vectors are made, the same thing, I calculate for each one of them, vectorize one by one, first 2 elements, the second 2 elements, third elements, and so forth. Do I have to change anything else? Huh? Then after that is the same, right? As Monte Carlo. I have to do frequency analysis and I have to do the plotting. So these things should be the same, right? So let's see if it works. I'm a bit nervous. Okay. Mode is not defined, that's correct. We just should be 2 values. Okay, frequency analysis, plotting. Okay. And then plotting PDF, CDF. Okay. And then the usefulness is that if you, for example, had half of the samples it should say, in principle, it should give you similar to Monte Carlo. Okay. It still is powerful to compute, to capture the variation. Okay. So that's another option you can use to solving the exercise. If you think it's too complicated, you know, just drop it and okay. Let's take a screenshot of that. Okay, so that's one of the changes we have made. You still have to make convergence. You have to make a convergence study, okay? But usually you need much less samples than Monte Carlo. Then we kept more or less the same, but I'm going to copy anyway. And here the main difference is this. Okay, this, instead of using the random, I'm using this new function that I created. Okay. And the rest is the same. Okay, remember that the number of beans usually has to be adjusted a bit with the number of samples. Okay, if I make 20 samples, I cannot have 20 beans. Okay, so it won't be realistic. So if I always should do some small adjustment of the number of beans. Okay, with the samples I have. NPU, I got similar, I think, number with half it number of iterations, like 80, and then I also add the CDF. Okay. More or less clear? Yep. Some of you say yes, some of you say no, but you think about it, do it yourself, and I hope, if you have any questions, we solve it during the exercise session, okay? But I hope you got like enough to start and you understand a bit the fundamentals of the method, okay? So there is another method, and with that we close the lecture. Okay, we have 12 minutes. So there is also, to reduce computational time, to reduce even further computational time, and also a very important thing is to include what we call integer or discrete variables. Integer discrete variables. It is possible to use probability trees. Okay. Has any of you used probability trees before? No? Yeah. They are typically used, for example, if you are deciding, right, to make an appraisal. Okay, you want to, or for example, you want to develop a field, or to simply to abandon, okay, to abandon the project. We have, in a tree, we make, this is a decision node, okay, this guy is a chance node, Okay, and this guy is an end node. Okay. So for example, I abandon and I simply don't get any value. Okay, my monetary value, MV stands for monetary value. It will be 0. Okay. If I decide to develop, for example, I might say I can still choose, right, between 3 options. For example, we can say this is the platform type. I can say FPSO, right? I can say I want to make a jacket, or I can say I want to use, for example, a TLP, okay, tension leg platform. Okay. So these decisions, I cannot usually deal with them with like a continuous, you know, when we're making Monte Carlo, we're sampling continuously. Okay. So these decisions, I sometimes better to use probability tree. Okay. After that, what kind of decisions chance node can I have? What could be a chance, okay, that I might have? You could say that I might have, for example, oil price, right? Oil price high, oil price medium, and oil price low. Okay? For example. And each one of them, the thing with a chance node is that each one should have an associated probability. Okay? PO low, PO high, and PO medium. Okay? And here you have probability 1, probability 2, probability 3. Okay? Or, for example, further, you might say each one of these ones might have a chance of getting N, right? Some amount of oil in place that I don't know. Okay, I might be lucky and I have a big reservoir. I might be lucky I have a small reservoir, and I might be lucky and I have a medium reservoir. Okay. Okay, so this is a bit more simpler to grasp. Okay, you simply say, for example, maybe $30 per barrel. Okay. You have maybe $100 per barrel, and then you have, for example, maybe $70 per barrel. Okay, and you talk to your economist, a guy that he's very brilliant, and he says, well, I have some crystal ball in the future, and he tells you the probability to be 30% is, for example, 0.4, is very high. Then the probability of being 100 is 0.1, and then the rest is here, 0.5. Okay. I assign it. Now, what happens with N? With N, typically, what do we have for N? Typically, we just saw it, right? We have something like this, right? So how do we include this guy here? Here has to be a set of discrete options, right? 3 options. How do we do it? Okay, and I might need all of these to calculate, for example, the monetary value. Okay, I decide to develop, I decide on the topside type depending on the oil price, which I don't decide, it's a chance, right? I might get high, low, or medium, and then finally I might have a big reservoir, medium, small reservoir. Okay. So how will you calculate all of these cases? Okay. So let's say case number. And we have to say topside type. And we have to say PO. And we have to say N. And finally, we compute for each one of them the monetary value. Okay. For example, let's say case 1 will be topside FPSO. Okay, and here I might have the price, oil price can be high. Okay, and the N could be, let's say, small. Okay, and then you calculate with all of that input, you say a monetary value. The company says, well, I have certain size, I can sell it by this price, and it's going to cost me so much. Okay, and I calculate the monetary value. Case number 2, what will that be? FPSO, again high, but now medium. Okay, and I calculate the value. Now, case number 3, FPSO, that will be again high, but now this one will be high. Okay. The 4th case, FPSO, this will be medium. Okay, oil price, and then the same thing here. Okay, I just copy all of these guys. Right? Okay, what else? Now we need for the low oil price, right? Low and low. And again, I also have these guys. These are all the branches in the tree, the calculation for all branches in the tree. Okay, what do I have to do now? Now I have calculated which branch? Yes. Only this branch, right? With all of these calculations from here all the way to here. Now I have to do the same for jacket, and I have to do the same for TLP. Okay? So here I have 5, 6, 7, 8, 9. Okay? Why? Because we had, and I see a similar for jacket and TLP. Okay, TLP stands for tension leg platform. We're going to talk about this hopefully next week. Okay, why we have 3? Because we have 9, because we have 3 cases times 3 cases. Okay, this is oil price times the N. Okay, cases. Okay. Another thing we have to compute, which is very important, is not only the value, but then we have the probability of each case. How do I calculate the probability of each case? Okay, let's go first on the tree. Okay, we say, what is the probability of each one of these occurring? No probability. That's something I decide upon, right? So this doesn't have any probability associated. This one, nothing, right? But now I come here. Which is the probability of each one of these 3 occurring? Here I have 0.5, 0.1, and 0.5. Okay? So depending which one I have, okay? So here it will be probability of oil price high, okay, times the probability of n, okay, of getting an n of this size, okay. Because each distribution, okay, this will be small. Each chance node, okay, in this case I have 2 chance nodes. I have the price and I have the n. Each node should have probability for each alternative. It must have, okay. And then that's telling me, at least for that branch, that I have a probability of, for example, 0.5 or 0.1 times, which is very small, times the probability of occurrence of such a, for example, a low size, which might be also small, okay. More or less clear? Okay, so we are going to talk next week on Monday a bit more on that. How do we evaluate projects using decision trees? Okay, but basically what you have to get the idea is that decision tree gives you values, right? The same thing that Monte Carlo. Monte Carlo allows you to compute a value, but also allows you to give a probability associated with each value.
Should we
Okay.
also multiply by P FPSO and P to develop?
Yeah, but they have no. These are chance. These are choice nodes. Okay. This is something I choose. They don't have probability. I can decide if FPSO, TLP, or okay. Okay, I hope it was more or less clear. Do we have any questions before we close? No? Okay, see you then on Monday, okay, for our early session at 8.